So the first thing that we're going to refresh on is, what does dissociation mean? We just got through a unit talking about how things dissolve and then dissociate. So how would we define dissociation? Yes.
When something breaks apart into ions.
Breaks apart into ions. Perfect. So this one says water dissociation. Water forms two types of ions when it dissociates. Dissociates means breaks apart. So this is going to be a little bit different than what we have practiced previously as far as what it breaks apart into. Oops. So the first one, can you name one ion that it breaks apart into?
Hydrogen.
And?
Oxygen. No, wait. Wait, I thought she was asking a question.
I was.
Yeah, she was. Yeah. Freaking corn dog. I'm just.
All right. Well, first of all, water is H2O, but we don't normally write it as H2O. How do we normally write it? So when we make it from a reaction, we would oftentimes write it as H and OH, which would lead me to believe that it would break apart into what and what? So hydrogen ions and what? Hydroxide ions. Okay, so the reason I'm writing it up here and not on A and B is because I wanted to kind of talk through it first. What really happens is that you do end up with your hydroxide ions, but then your hydrogen ion basically attaches to another water molecule, and you end up with what is called hydronium, and that is H3O+. So when a water molecule breaks apart, it will dissociate into hydronium, which is like water but has another hydrogen ion attached to it, so it's going to be H3O+. The plus is a +1 charge. And hydroxide. I'm going to put on this or hydrogen +1. We show it both ways. So I'm going to kind of jump down to tie this to this bullet point. It says, note that H3O+ is called hydronium. And it is an ion that is used interchangeably with H+. And then as a reminder of what an acid is, do you remember how we defined those? An acid will be a compound that, what? Bless you.
Dissolves water.
If I give you a list of compounds and said, circle the acids, how would you know which ones are the acids? Not just have hydrogen, but specifically starts with hydrogen. So a compound that starts with hydrogen. This is because all acids, when dissolved in water, so I'm going to make this a little thinner so I can write better. When dissolved in water, they will form H+ or H3O+ ions. So an acid is going to be anything that starts with hydrogen that when it dissociates, when it dissolves in water, it's going to form these ions. And then a base is going to be defined a little bit similarly. I'm going to change the color to blue. I tend to use red for acids, blue for bases, and we'll see why when we get to the indicators page, but it doesn't really matter. A base is a compound that ends with OH. Actually, just for the sake of being consistent, I'm going to say ends with, and I'm going to spell out hydroxide. But that I'll put in parentheses is OH minus 1. The reason we say that it ends with hydroxide and doesn't start with hydroxide is because when we form an ionic compound that contains hydroxide, since hydroxide is negative, it would be the second thing that's in the compound. So when this is dissolved in water, this forms OH minus 1 ions. So an acid will form H plus or H3O plus ions, and a base will form OH minus 1s.
Why do we write it like HOH?
Because when, you don't have to, when we typically are creating new compounds from an acid-base reaction, which is normally how we're forming water, it would be that you're bonding your positive hydrogen cation with your negative hydroxide anion. But you don't have to write it as HOH, it's just how we've seen it a lot. It also helps a lot with balancing. So if you go back to our balancing unit, we broke it up into hydrogen and hydroxide because it made it easier for balancing. All right, and then this whole section is a review from our nomenclature unit. We used this exact same chart, these exact same examples, everything is the same. So let's just refresh. First of all, in this box up here, this is how you can tell that something is an acid. So if you're looking at the formula or looking at the name, how can you tell that something is an acid? Starts with H. So formula starts with H. If you had something like CH4, is that an acid? No, because it doesn't start with hydrogen. Even though it has hydrogen in it, that doesn't start with it. So that is not an acid. The reason that that won't be an acid, if you're curious, is if I had CH4 and I were to draw that, this is a covalent compound because I have a nonmetal and a nonmetal, they would be sharing electrons, and so this ends up looking like this. You don't have to draw this one. I don't want you to get confused. I just want you to see that not every single thing that has hydrogen is automatically an acid. So CH4 would look like this if you draw it. When you put that into water, first of all, it's not going to dissolve because it's nonpolar. Second of all, it's not going to ionize. It's not going to dissociate because it's covalent. It's not forming ions. Make sense? Okay. So if the compound starts with hydrogen, that would make it an acid. And then if you're looking at the name of something, how can you tell by the name if it's an acid? Does it have to start with hydro?
No.
What do all acid names have in common?
Give me a second.
The end of the name ends with acid.
The end of the name ends with acid. Who'd have thunk he got it right? All right, yes. So it literally has the word acid in it.
What unit were we talking about acid?
Nomenclature, I think, was maybe unit,
It was nomenclature.
was it 9?
It's 8.
8.
Acetic acid.
Oh.
Hydrochloric acid.
Yes.
Polyamine.
Yeah, this is our last unit.
I know, it's so sad.
Are you sad?
Yeah, because you're gonna leave. That's so sad.
Wait, do I have to go to Turner next year, or can I get to different school?
Huh?
Am I the one who decides that?
No, I'm saying like, from already sophomore year to Turner, I could just change schools, right?
Yeah. Bye.
Yeah, I can switch.
Just playing Thomas was nice.
I don't understand how I have anything to do with that decision.
I was just asking from the teacher's perspective. It's like, I didn't know if that's a thing or not.
Leaving the school?
Yeah.
You're allowed to do that
Okay, I didn't know.
with your parents' permission.
I need different teacher. I could be your friend. Yeah, this is my guardian angel.
All right, so if you have a compound that starts with hydrogen, it has acid in the name, you know that it's going to be an acid. And if it starts with hydrogen, it's either going to be hydrogen bonded to what or what?
Wait, say that again?
What would hydrogen be bonded to? So if your compound starts with hydrogen, it's going to be H bonded to,
Bonded to a single element?
Yes.
Polyatomic ion?
bonded to a single element. Or if it's not bonded to a single element, that means it's bonded to multiple elements. So H bonded to polyatomic. All right, if you are hydrogen bonded to a single element, our naming convention for that one is when we start with the prefix hydro. So we would say use prefix hydro. And then you'll change the end of what we'll call the element root to ic. So your convention would go hydro, blank, ic, acid. You always add acid at the end. So hydro, something, ic, acid, where in that section, in the little blank, that would be your element root. Ooh. So hydro, something, ic, acid. And then there are kind of two exceptions to this. One is that you use the whole element name for phosphorus and for sulfur. So for phosphorus, and for sulfur, keep name until the R. So here or here. So if you had, for example, hydrogen bonded to phosphorus, you would call it hydrophosphoric acid instead of just calling it like hydrophosphoric acid. Same thing with hydrogen bonded to sulfur, it would be called hydrosulfuric acid, not hydrosulfic acid. Make sense? Is this refreshing your memory? Maybe bringing back some PTSD of the daily quizzes?
I was eating this
That was
section
hilarious.
All right, can I scoot this over? So if you are hydrogen bonded to a single element, that is the only time that you use the prefix hydro. So we are going to explicitly write in the other box that if you are hydrogen bonded to a polyatomic ion, you do not use prefix hydro. Do you use the word acid in these? Yes. Okay, so make sure you add the word acid. So for polyatomic ions, this is where we had the thing that sounded like a disease. Remember, we called it adic-itis. It's when the polyatomic ends in the letters ATE, you are going to change it to IC. And if your polyatomic ends in ITE, you're going to change the ending to OUS. So change the ending of your polyatomic ion based on whatever it is. And then, add acid to the end. And then I do want to make sure that you recognize that this same little exception down here for phosphorus and sulfur will also apply to polyatomic ions that have those in them as well. So for polyatomics like phosphate or phosphite or sulfate or sulfite, you need to add the R back in from the element name. Meaning, if you were going to change ATE, so normally if you had an ATE polyatomic ion, you would change that ending to IC, so it would sound like it's going to be phosphoric acid, but you're putting the R back in it so that it's phosphoric acid. With phosphite, ITE, you would normally change it to OUS, so it looks like it would be phosphorus acid, but it's going to be phosphorus acid with an OUS. Sulfate, you would call it sulfuric acid, not sulfic acid. And then sulfite would be sulfurous acid. So you put the R back in it. Otherwise, it's a pretty straightforward swap where you just take off that ending and replace it with a different one. So I'm going to give you a minute to practice anything in this section. So for part C, you're going to tell me the names of each of these elements, and then you're going to write the formulas for each of these elements. Don't forget that when you are writing the formula name, write the formula from the following name. Sorry, when you're writing not the formula name, but the formula, don't forget to crisscross. So crisscross their charges. Hydrogen always has a +1 charge, so you don't really get an extra subscript from that one, but sometimes you need to put a subscript on it like this. So that 3 came from crisscrossing from phosphate. So I'm going to pause here real quick, give you a second to work on that, and then we'll come back and check our answers. Ask that again.
What's the point of crisscrossing? I don't get it.
To make the charges even.
So crisscrossing it is our shortcut method of being able to determine the ratio. So remember, when you have this ratio, when you have HF, for example, it's a 1-to-1 ratio. Because hydrogen has a +1 charge, fluorine has a -1 charge. So when I put them together, those charges end up being neutral because the +1 and the -1 balance each other out. Hydrogen needs to lose an electron, fluorine wants to gain that electron. It works beautifully for them. Our shortcut to mathematically figure this out without having to draw it and figure out whose electrons are going where is the crisscross method. So if I have hydrogen that wants to lose an electron, hydrogen normally has 1 electron and wants to get rid of it, versus I have, versus if I have phosphate, there we go, versus if I have phosphate, PO4 with a -3 charge, phosphate is going to get its -3 charge by gaining 3 electrons. So if I have this that wants to lose 1, I would need 3 hydrogens to get it to gain 3. So we can use the crisscross shortcut to figure out the subscripts that we need. This is the same way we've made any ionic compounds all year long. Okay. I'm going to cut off this video here and then move on to bases in the next one.